All right. So it is a pleasure to introduce, as you see, Konstantin Aleshkin from Columbia University. Tell us about what was the project central charge.
Thanks for introduction. Thanks for invitation. It's nice to be here. My first time here. So I want to talk about some project. So it's based on ongoing work with Melissa Williams, also from Columbia. And so, I wrote a paper last year about this. It's called part 1. We're currently revising it, and so I plan to continue this discussion. So actually, I'm learning part of the story myself, so please ask questions. So I'm also not sure how much or how little should I talk about. So, hey, what is this about in general? So in general, the picture that we will have some x, which is going to be the same projective storage instead. Or in fact, this is going to be a GIT quotient of a vector space, vectors. So this is finite dimensional of a vector space. This is going to be a complex storage function, going to like a U1 power k. So this is same projective storage instead. And so the idea is that GIT quotients, they naturally, so what's the GIT quotient? So GIT quotient is associated with some choice of stability conditions. So this is omega is a G character, and the rational G character. So stability condition. And different choice of stability conditions possibly yield different spaces X. Like the gold section. For different omega, we get different X. So yeah, this case is very simple. Of course, the GLJT story is much more complicated. So this is some plain model, some story where we can change some phenomenon of J-table crossing. And by J-table crossing is the following. So space of stability conditions. So space of rational G characters naturally split into walls. Sorry, into chambers by some walls. So and then all x omega for omega in a given chamber are essentially the same. So isomorphic algebraic variety for the same asymplectic variety, and only the Taylor form of the symplectic variety depends on this omega. So here we'll have some toric orbifold x plus, here we'll have some toric orbifold x minus. And so the wall crossing I'm going to talk about today is the wall crossing between these two different models. So now what are the objects I'm gonna talk about? So it's elliptic central charge. So we call this as a generalization of what is called the quantum cohomology central charge. Or an object mirror to a period integral of a Calabi-Yau manifold or a Landau-Gilbert model. And so what is this elliptic central charge?
I don't think it's a good idea.
Oh, okay.
To direct, because I'm quite certain it will break.
Oh, I see. Right. Yeah, that's very
In my
stable.
experience, suggests.
So, in formula, this elliptic central charge is a generating series of invariants. Generating series of enumerative invariants of X, and those enumerative invariants are going to be quasi K-theoretic quasi-map invariants. Associated to an elliptic cohomology class of X. Equivariant, elliptic cohomology class of X. So these objects are going to solve some Q difference equations, which is analog of differential equations that are solved by usual quantum cohomology central charges. And so the idea is that these elliptic central charges are going to have integral representations of main branch type, and one can expand them in either chamber of parameter, and then they'll reproduce elliptic central charge of some elliptic cohomology class for X plus or for X minus. So this is a very rough idea of what's going on in the picture.
So do this differential equation have symptoms?
So it's a Q difference equation. So this is like in quantum cohomology, the both small and big I function, they satisfy differential equations in Novikov variables and in cohomology variables. In quantum K theory, I think about it as so the quantum K-theoretic I function satisfies Q difference equation in the Novikov variables, but still differential equation in the K-theory variable.
So you do have symptotics and they coincide with the basic asymptotics of the quantum theory.
In principle, they should. I shouldn't say too much because so I'm interested in Novikov variables, and then the limit can be a bit tricky, especially when there are orbital flights.
So K-theory has torsion, which homology don't.
Right.
Does this equation pick up the torsion?
No. So this is actually everything is over psychology. So because also in my approach to elliptic cohomology, it's also is approach over C. So the approach to elliptic cohomology I take is equivariant elliptic cohomology. Over C. And so this is wholly works of Rognovsky, Ginzburg, Kapranov, and Serov.
So how did you pronounce Jan's name?
Huh?
How did you pronounce Jan's name?
Rognovsky?
Gradinovsky.
Okay, great. Yeah. I should know better.
Should be easier for you.
Gradinovsky, yeah. Sorry about that. So, and then, so more maybe in even closer by spirit to what I do is the approach developed by Hakanagi Chukunkov. In the work of elliptic stable angle. So what is the idea? let X, Y be a G pair, with a pair of topological spaces. So Y is subject of X. With G actions for in principle it could be any compact Lie group, but for today it's going to be just a torus. So I'll not distinguish between a compact Lie group and its complex algebraic version. So for me, G is going to be U1 to some power or C star to the same power. So then, well, G equivariant. So in principle, those has to be not just topological spaces, but those has to be an equivariant version of CW complexes. But so let's look through the details and the carbon. So G equivariant elliptic cohomology in the language of this framework is going to be a covariant functor from pairs of topological spaces. So I call this L sub G. And so it sends it not to, so usual cohomology theory can be rephrased, or K-theory can be rephrased as a functor from pairs of topological contravariant contravariant functor from pairs of topological spaces to abelian groups, to define some axioms. So elliptic cohomology in this framework is functor not to the abelian groups, but instead to sheaves over some scheme. So scheme, which I'll call L sub G of X, and a sheaf on the scheme. And this is going to be a scheme over a scheme that is identified with elliptic cohomology of a point, which I'll also denote as E sub G. Satisfying some axiom. So let me discuss this construction a little bit. So what is equivariant elliptic cohomology of a point in this approach? So this should be a version of elliptic version of. So as I said, this is a scheme. So this approach is dual to the usual approach to the cohomology. So this should be an elliptic version of the spectrum of the usual equivariant cohomology ring of a point. Or maybe equivariant K-theoretic point. So, well, equivariant cohomology, equivariant K-theory is a ring. The spectrum is an affine scheme. Whereas equivariant elliptic cohomology is going to be a project. So consider the case where G is C star to some power. So then spectrum of equivariant cohomology of a point So what is the equivariant cohomological point? Is a free algebra over the equivariant variables of the stores T. So this is just going to be naturally identified with the Lie algebra. So the variables of the algebra can be thought of as elements of H2 of classifying states of T, which are naturally first Chern classes of equivariant line bundles over the point. Well, then what is the spectrum of T equivariant K-theoretic point? So what are elements of the equivariant K-theoretic point? Those are basically representations of T. So since T is a torus, a representation can be decomposed into one-dimensional representations. And then this ring is a Laurent polynomial ring generated by characters of T. So the spectrum of K theory is naturally identified with T itself. So now what is going to be the elliptic cohomological point? So maybe before I introduce elliptic curve.
What is the Chern character map?
The character map is just the log. Oh, sorry, exponential, right? Other way around. All right. So so for this, usually when people talk about elliptic cohomology, people are interested about thinking about like how elliptic cohomology varies when we change an elliptic curve to define elliptic cohomology. However, for today's story, this is not important, so we can fix an elliptic curve, single elliptic curve over C. So for today, the elliptic curve is just going to be a C star quotient Q power Z, where Q is, you can think about Q as a complex number, which is the same as C modulo lattice, 2 pi I, Z plus tau Z, where Q is e to the 2 pi I tau, right? So this is a very naive approach, because usually elliptic cohomology becomes interesting exactly when becomes interesting exactly when you consider some interesting timeless of elliptic curves.
So tau is going to be fixed here. Tau is going to be fixed.
Right. So we can just fix tau. Because this story about crossing, it actually it's true for every elliptic curve. So one can just fix it. Okay. So I'm going to think about Q as a formal vector and consider this form. So right. Then the elliptic cohomological point by definition is going to be C quotient the Q, the power of the co-characters for one parametric subgroup. So for example, if T is just a star, then if the star of a point is just going to be, well, the star quotient Q to the power of co-characters of the star, which is just Z. So just the elliptic curve itself. And so if we have an isomorphism between T and C star for the K, then elliptic equivariant cohomological point is going to be isomorphic to K copies of the elliptic curve. So, and now, the way I think about this is, if we want to talk about elliptic cohomology classes, well, what are the usual cohomology K-theoretic classes? Those can be thought of as functions on or sections of the structure sheaf of the corresponding schemes, the algebra or just the group itself. Whereas, since elliptic cohomology point is a projective scheme, there are no non-trivial global sections, so elliptic cohomology classes are going to be sections of some non-trivial sheaves over the elliptic cohomology scheme. Right. Yeah, so this has been defined as like for all complex Lie groups, but today we'll stick to this case. Now, how do you construct the elliptic cohomology of X now? Once we have elliptic cohomology for point. Well, construction of Grainovsky tells that analytic locally over ET, so elliptic cohomology for point. So any neighborhood inside ET is isomorphic to analytic neighborhood, small analytic neighborhood, isomorphic to analytic neighborhood in T, because this is just a quotient of T by lattice. It is also analytic local isomorphic to the algebra. And so over the Lie algebra of T, we have the spectrum of equivariant usual cohomology of X. And so analytic locally, the equivariant elliptic cohomology is going to be the same as the usual cohomology. Let me write this in more detail. So the same as and for simplicity, I assume that X has no odd cohomology, which will be the case for toric varieties. That's what I expect. And spectral. What does it mean? It means that, so consider the elliptic cohomology scheme of a point. And then let A be a point in this elliptic curve, or product of elliptic curves. Then we can take an analytic small neighborhood, U, and analytic small neighborhood there is the same as neighborhood on our Lie group T. So I can think about this here as a subset of T, right? And then there is a Chang character map, the log map. And so I want to center it at this point A. So I'm subtracting Chang character of this point A. I'm mapping to the algebra of T, which is a spectrum of equivariant elliptic cohomological point. And so over here we have spectrum of usual equivariant cohomology. And so what one would want to make is something like this lines. So this P. So this is going to be elliptic cohomology of X. So one would like to have just going to be P minus inverse of P. One want to have those coinciding. So the problem with that is, if you have a point in elliptic cohomology of a point, Well, this defines your point in T modulo character length. So you don't know which point in here will you use to construct this diagram. So the correct way to remedy this definition is to consider the let me take this picture a bit more.
Yeah.
So the correct way to build elliptic cohomology is to consider here the equivariant usual cohomology of some subset of X, so where X dA is a fixed locus of a subgroup TA. So TA is a subgroup of T, which is intersection of kernels of all the characters that are trivial on our point A. So what does it mean? So usually we have very general localization in K-theory. So if you have an equivariant K-theory of X, and then you invert a finite number of elements, it will localize it. This is going to be isomorphic to K-theory of the fixed locus. And so over the generic point that is of A in here, which is not killed by any characters, the spectrum of K-theory of X is going to be the same as the spectrum of K-theory of the fixed locus. However, for special points, what could happen is that, well, some of these characters with respect to which you have to localize, they will vanish at this point. And so that's why we have to do this.
Sorry, may I ask what is X? I just missed the.
Right. So
what's the background of X?
right. So for today, X is just a genetic quotient vector space, except for
The one from the.
yes. So in principle, this theory is much more general, and X can be just a G covariant CW complex, and T has not to be doesn't have to be torus, but right. So I have 1 hour, right?
Yes.
So now I'm going to specialize and go through this construction in the very simple case, where X is going to be actually a genetic quotient with respect to T star to see what happens. And try to compute elliptic cohomology of X and see how it goes. So let V be just a this n-dimensional vector space. And the torus T with respect to which we're going to compute our equivariant elliptic cohomology is just going to be the maximal torus in GLV. So it's star to the n. And we're going to discuss the equivariant elliptic cohomology of X with respect to T. So first of all,
What is omega here?
right, so omega is a rational G character. In this case, it's just a rational number. and this is the stability condition. So for here there are two choices. So essentially two choices. So this is the space of stability conditions. And as I said, there is a wall chamber structure. In this case, this wall chamber structure is just positive and negative numbers. So essentially, I'll call it x plus and omega negative. So x is equal to x minus. So now, so this bracket over here, it signifies that I'm taking the stack quotient, so slightly different than usual definition of the JT quotient. So let me just write around the definition. So this is